Welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, we say we do enjoy solving the harder problems, but above all, we see and appreciate the beauty in the simpler problems. So today we're still on the MIT 2022 Integration B regular season. We move to part two, where we're still focusing on the trigonometrical functions as regards integration. So today we look at four questions. Yesterday we looked at one. Today I thought we could bunch a few and at least have some headway into it. The first problem that we'll look at is problem number 5 in the regular season competition, and that is the integration of 2020 sine to the power 2019x times cosine to the power 2019x minus 8084 sine to the power 2021 x times cosine to the power 2021 x. Very interesting. The next question is the integration of 1 over sine to the power 4x times cosine to the power 4x. Problem number 8 is our next problem, which is the integration of x plus sine x over 1 plus cosine x. Problem 11 will be our last problem in this part, where we'll look at the integration of cosine x minus sine x over all that over 2 plus sine 2x. So before we jump into looking at the solutions for these problems that look quite intricate, I would like to thank our subscribers. Thank you so much for entrusting us with the support. We don't take that support for granted. And our way of paying back is by showing up day in, day out to come up with solutions to some of these seemingly harder problems. For those of you who are here for the first time, we really would encourage you to subscribe to our channel. We like your support, and we'll really make use of that support going forward. And in return, as we said, we'll come here day in, day out and share with you some of our solutions to the problems that we think are harder. And if you're here for the second, third, or fourth time, but are on the fence about subscribing to our channel, we'll keep coming up with these solutions. And one thing we could say is that we'd like to win your trust and your support. But other than that, it is an absolute pleasure for us to be here sharing with you these solutions. So I'm going to jump into the solutions. Problem number 5, which really looks complicated, is the integration of 2020 times sine to the power 2019x times cosine to the power 2019x minus 8084 sine to the power 2021x times cosine to the power 2021x. I'd like to look at the integrand a little bit closer, and then see how we can simplify it and make it visibly an integratable construct. So first thing is I see that, and then I'm like, okay, so how do I combine these two terms? Somehow in my mind, I have this intuitive feeling that there is a way I can combine these two expressions so that I have a differentiation of product formalism so that I can easily integrate. So one way is I see there is a difference of about 3, actually 2. And what I would do is I see sine squared plus cosine squared x is equals to 1. I would like to plug that in somewhere so that the powers are kind of related. And then if I square sine squared x plus cosine squared x is equals to 1, we get this expression sine to the power 4x plus cosine to the power 4x plus 2 sine x squared times cosine squared x is equals to 1. So if I plug that right after that first term, then we get that 2020 sine to the power 2019x times cosine to the power 2019x can be multiplied by sine to the power 4x plus cosine to the power 4x plus 2 sine squared x cosine the power cosine squared x. And then the last term can be kept as it is. So multiplying this initial term across, so we have the power sine the power 4x times sine the power 2019x results into sine the power 2023x. Cosine x for that first term remains as it is, but the second term now lifts the cosine the power 2019 from that to 2023x. And then this third term now combines that to now 40,040 sine the power 2021 x cosine the power 2021 x. Now you see these powers, second, last, and last term have the same powers all through. So this one now reduces this constant 80,084 down to 4,044. Right? Now we have to now try to pair terms up so that we can see a relationship that tells us there is a differentiation of our product. So the next thing I would do is since we have 2023, 2019, and as you can see here, 2019 and 2020 seems like this cosine term was differentiated to create this constant here. And similarly, we can see that for 2020 here, this sine term was differentiated. Now, the next thing is, then I'd like to pair this, because when you have the product of two terms, you have to also have a second term. For example, we have to see when 2023 is factored into the differentiation, right? And that is done by splitting this into 2022 two times. So I have 2022 sine to the power 2021x times cosine to the power 2021x brought forward here. And then the next 2022 is left here, and that now is left to interact with this second term. So as you can see here clearly, this here is sine to the power 2022x negative times the derivative of cosine to the power 2020. And that results into cosine to the power 2019 times sine x, which now again causes the 2022 to be lifted up to 2023. And then the second term is the same cosine to the power 2020 times the derivative of sine 20 to the power sine to the power 2022. And the same process repeats for the second one. Here we start with sine to the power 2020 the power 2020 times the derivative of cosine to the power 2022 plus the derivative of sine to the power 2020x times cosine to the power 2022. So this means that we just have a negative of the derivative of sine to the power 2022x times cosine to the power 2020x plus the derivative of sine to the power 2020x times cosine to the power 2022x. So we can bunch all that together so that the expression above is the same as just the derivative of sine to the power 2020x times cosine to the power 2022x minus sine to the power 2022x times cosine to the power 2020x. So we plug that into our integrand. So our integrand here that was initially given in the question is the same as the derivative of this expression here. So when we plug that in under the integration sign, what that means is that our integration now results in this expression inside the differentiation function. So now our integration is sine to the power 2020x times cosine to the power 2022x minus sine to the power 2022x times cosine to the power 2020x plus a constant c. And that is the answer that was expected. Our next problem is problem number 7, which is 1 over sine to the power 4x times cosine to the power 4x. So we could quickly re-express this as sine 2x over 2 to the power 4 in the denominator of the integrand. And so that means that that 2 to the power 4 becomes 16, and that now goes into the numerator. And we can pull that constant out such that we have 16 times the integration of cosec of 2x. Now, this is the same as cosec squared 2x times cosine squared 2x. And then we can play around with 1 over cosec squared 2x such that it is cosec 2x times cotangent 2x plus 1. And so when you multiply the cosec squared 2x times the cotangent squared 2x plus 1, you have cotangent 2 to the power squared 2x times cosec squared 2x plus cosec squared 2x. And this is the same as the derivative of negative cotangent cube 2x. Now to negate, because that we don't have a 3 here, now that means that original function has to have a denominator of 3. And then since we are also dealing with 2x instead of just x, then we need to have a denominator of 2 here. So this is the integration of this first function, and also cosec squared 2x. To take care of the 2x here, we have a negative half. And so now our integration is negative 8 over 3 cotangent cube 2x minus 8 cotangent 2x plus c. And that is our answer. Very interesting. Then problem number 8, which is x plus sine x over 1 plus cosine x. One of the things we could do is express it into the half angle formalism, so that in the numerator we have x plus sine 2 sine x over 2 times cosine x over 2. And then the denominator, that is 1 plus 2 cosine squared x over 2 minus 1. And so this 1 and this negative 1 cancel each other out. And so we have x plus 2 sine x over 2 cosine x over 2 over cosine squared x over 2. And so this becomes x over 2 sec squared x over 2 plus tangent of x over 2. Now a half of sec squared x over 2 is the derivative of tangent of x over 2. So another way we could represent that is that is the same as x times the derivative of tangent of x over 2 plus the tangent of x over 2 times the derivative of x. So that looks like a derivative of a product of two functions, x and tangent x over 2. So if we express this as the integral of the derivative of x at tangent x over 2, then it means the answer to our integration is x tangent x over 2 plus c. That is the expected answer. Now, problem 11, cosine x minus sine x over 2 sine 2x. As you can see, this is a little bit complicated. This problem could be expressed as cosine x minus sine x over 2 plus 2 sine x cosine x, just trying to expand the sine 2x term so that everything is in the same angle format, that is x. And so we can say let cosine x plus sine x, let u be equal to cosine x plus sine x. And there's a reason I'm trying to put that substitution, because I want to simplify this denominator. Since if we differentiate that cosine x plus sine x with respect, if we differentiate 2 with respect to x, we get cosine x minus sine x dx as a substitution for du, which is exactly what is the numerator. And since we also know cosine x plus sine x squared is equals to cosine squared x plus sine squared x plus 2 sine x cosine x, and since cosine x squared plus sine squared x is 1, we have 1 plus 2 sine x cosine x. And then on the left-hand side, we have u squared. So essentially, sine x cosine x is u squared minus 1 over 2. And so we can plug those substitutions into our original integration. So cosine x minus sine x would be dx would be du, and then the denominator would have 2 plus 2 well, let's just simplify this. This 1 plus 2 sine x cosine x is the same as u squared, and the numerator is the same as du. So we have a simplified problem, which is the integration of du, the integration of 1 over u squared. And so if we let u be equal to tan theta, such that du d theta is sec squared theta, and so du is equals to sec squared theta d theta. Our integration of 1 over 1 plus u squared is the same as sec squared theta d sec squared theta over 1 plus tan squared theta. And so what that means is we have sec squared theta in the denominator, which cancels out the numerator, and so we are left with the integration of 1, and that is same as theta plus c. And since we set tan theta to be equal to sorry, I missed u here, then it means that theta is the arctangent of u, and so the integration of 1 over 1 plus u squared is the arctangent of u plus integration constant. But also, since we set u to be equal to cosine x plus sine x, and it means that the original integration is the arctangent of cosine x plus sine x plus constant. This is very, very complicated, but very interesting problem. So I think that brings us to the end of today's problems. I hope you've enjoyed following through. It has been an absolute exhilarating process for, just us going through these solutions and also sharing this with you. Thank you so much. If you've forgotten and you are inclined, please subscribe to our channel. We look forward to continuing growing with you. Bye-bye until next time.